So now we've talked about process yield. We'd also like to discuss 3 more ways of measuring defects. And the first one is the parts per million, or ppm. Now before we had denoted P as the number of defective units over the total number of produced units. ppm is the number of defective units per million. So the number of defective units in 1 million produced, or can also write as the fraction defective, P times 1 million. Now you hear ppm typically used in scientific fields like chemistry as a way of quantifying very, very small volumes, but you also hear it quite regularly in quality management. So as an example, for a 99.379% yield at each step, what is the ppm? Well, we have the yield at each step is going to be then 0.99739, which is equal to our 1 minus P. Then P is going to be equal to 1 minus 0.99739, or 0.0621. So the parts per million, as we said, we take that fraction defective, P times a million, and we end up with 6,210 parts per million defective. Another example then, if we have 99.99966% yield at each step, what is then the parts per million? So again, the yield at each step is going to be 1 minus 0.99966, or sorry, 1 minus P is equal to 0.9999966. P is going to be equal then to 1 minus that, or point, and here we have 5 zeros, 0.00000034. Parts per million then is going to be 3.4 parts per million defective. So closely related, of course. Now, we have our car example. If we have a car consisting of 10,000 parts and production processes, and if we have 6,210 parts per million defective for each of those process steps, or for each part, this then means our overall process yield, as we said before, is going to be 0.99379 to the power of 10,000. So again, we took our fraction defective and we converted that then into the 1 minus P, and all of our vehicles will be faulty. On the other hand, if we have 3.4 parts per million, which translates into this 0.00000034 fraction defective at each process step or for each part, then the overall process yield, of course, is 1 minus P, so it's going to be the 0.9999966 to the power of n, 10,000, or as we saw before, 97% fault-free vehicles, good cars. So let's just make one point before we move on. There's a distinction we're making, if you've not picked it up already, between defects and defective products. Now, we said before, a defect occurs when the outcome of a process or process step is not what we expect. Let's look at another example here. I produce pencils and I produce high precision drills. If I produce 1 million pencils and 1 million drills, and my pencils have 30 defective units, then my parts per million, since I produced 1 million, is going to be 30 parts per million defective. My drills have 3,000 defective units, defective drills. I'm going to have a ppm of 3,000 parts per million defective. The question is, are my drills worse than my pencils? So here I've written it again. Let's look at our yield. So the yield for the pencils, so we know that the parts per million divided by 1 million is going to be P. So the yield is 1 minus P, and we end up with 99.997% yield for our pencils. The drills, on the other hand, again, this is P, we end up with 99.7% yield. And so clearly this is higher. Clearly the yield for the pencils is higher, but are the drills worse than the pencils? And now we come to the concept of DPU and DPMO. If the drills have many more opportunities for defect creation, then the defect per million opportunities measure can actually be the same or even better for the drills. Let's have a look. So first of all, defects versus defective. A defect occurs during any process when the outcome of the process is not our expected outcome. It's a flaw, an error, a discrepancy. There can, however, be multiple opportunities for a defect, and so an item is only said to be defective when there's a decision made that the item is not acceptable. And this can be based on one characteristic or the accumulation of multiple defects making our characteristics unacceptable. To take this into account, we define additional measures, the DPU, or defect per unit, which is the average number of defects per unit of product, and the DPMO, or defects per million opportunities. The DPU metric is a measure of capability for discrete or attribute, we'll learn later, data defined by the following: the total number of defects divided by the total number of units. So you count the number of defects produced. And this could be, for example, the pencil could have defects such as the length, it could be too short or too long, could be the diameter, could be too thick, too thin. Blemishes on the paint, for example, the eraser is fitted too tightly or too loosely. We can count these defects. We count them up and we divide that by the total number of pencils to get the DPU. The DPMO, or defect per million opportunities, is a metric which differentiates between products with many defect opportunities, like our drill, and those with very few defect opportunities, which is our pencil in this example. If each unit has several opportunities per unit, so critical to quality characteristics, to be defective, then we can talk about DPO as the defect per million opportunities equal to our DPU times a million divided by the total opportunities for a defect in one unit. And that then translates into the total number of units, the total number of defects divided by the total number of units, which is here then equal to our DPU. Now, how do you make this decision of how many opportunities we have for defects in a unit? And this is where the softer side of quality comes in. Your team decides. How many defect opportunities do you have in a pencil? How many defect opportunities do we have in a drill? What happens then if your team selects more than one opportunity for defects? So clearly, if you think from between pencils and drills, this number will change. This is the decision here. If you think your drill has more opportunities, then this DPMO number will be reduced compared to pencils. We're going to look at an example of this. You are influencing here the numbers. So here we have two processes, process A and process B, and we're going to process 10 units through each. So here we see process A with 3 steps, and Unit 5 comes out bad, so we have a process yield of 9/10 or 90%. For process B, 10 units, and Unit 1, Unit 2, Unit 8, Unit 5, Unit 8, and Unit 10 are bad. So we have only 5 out of 10. So process yield for process B is only 50%. So based on the process yield, you can see process A is better than process B. Maybe they had a different machine. Maybe they used a different operator. So you're not sure what the processes should be the same. Let's look now, though, at the DPMO for each of these processes. And now we have to introduce actual defects. So we have each unit has 8 defect opportunities. And we indicate a defect by this little red dot here. Here we see for process A that we have one, remember for process A that Unit 5 was defective, and all of our defects have occurred on Unit 5 and it's officially defective. For process B, however, we see that the defects are actually on each of the defective units. Each of these defects caused a defective unit, but they all occurred on different units instead of all in the same one. So if you look at the DPMO for this, don't forget DPMO is the total number of defects times 1,000,000 divided by the total number of units times the total opportunities for defect in one unit. Both processes are generating 5 defects. Here are 5 defects, and here are 1, 2, 3, 4, 5. So for process A, DPMO, total number of defects is 5 times 1,000,000 divided by the total number of units divided by the total number of opportunities for defect in unit, and we said that was 8. So we end up getting 5 total number of defects times 1,000,000 divided by the 10 units times 8. We get 62,500 as our DPMO, defects per million opportunities. And for process B, lo and behold, we get exactly the same thing, because we still have 5 defects for process B. So we see with DPMO that the processes are equal. Both generate the same number of defects, even though the number of defective units that came out of the entire process is clearly not the same for A and B. So let's just make a couple more notes here. What is the difference to PPM? Here, we're talking about defects. We're not talking about defectives. In PPM, we say, well, in DPMO, we're saying the parts or processes can have more than one defect opportunity. More defects can occur and create one defective. Parts per million, which is the number of defective units per million units. So you're looking at the defective units that are coming out of the process. Now, these are often used interchangeably in industry. And we're going to look at this again in the context of Six Sigma. So just to recap, if P is the fraction defective, the number of defective units over the number of produced units, we have yield is then going to be equal to 1 minus P. It's the number of good units produced at process step versus the number of total units going in. If we have more than one process step, I could write this down here with the process yield equal to 1 minus P to the power of N for the same yield loss at each step. PPM is P times 1,000,000, and DPMO we saw is this DPU times 1,000,000 divided by the total opportunities for a defect in one unit. Now, if there's only one defect possible per unit, and that creates a defective, then you'll end up with DPMO equaling to PPM. You would then say that the number of defects is going to be equal to the number of defectives. There's only one opportunity and it causes a defective, then you get DPO equal to DPM. Let's look at measuring the defect rate. So why don't we just measure the defect rate directly? Well, first of all, the defect rate is hard to measure when defects are rare. And what we're going to be trying to do is to identify a key variable. We call this critical to quality variable for the product. We want to measure this variable to help us monitor our defect rate. If this variable moves out of specification, then we expect a defective. And we're going to call this then the critical to quality, or CTQ variable. The distribution of this key variable and its relation to the specification limits, our expected outcomes, will offer us insights into how the defect rate, the fraction defective, can be reduced. For example, as we'll see later, targeting the mean and reducing the variation, or both. We're also going to see that measuring the distribution of this key variable can be very straightforward when you're using, for example, the control charts that we see later in Six Sigma. And that will then also bring us to our next section in this course on process capability. And what can we do about defects? Why don't we just measure them? Well, as we just said, it's hard to measure them when they're rare. They also can have many, many different causes. So one thing to do is to try to detect them early. Early detection is better than late detection or inspection. Why? Well, we talked about that with our crayon factory. First of all, we're losing our cost of our materials for any defective that's produced, and we're going to be then using even more capacity and manpower if that defect continues through the process. And if it's detected early, then the idea is that we can quickly look into it, reduce the number of defects. We can then get rid of those defective parts with defect, and the capacity can be increased, and we'll reduce all those internal failure costs that we talked about. That's what we just said. The cause hopefully can be identified. We don't have to look through the entire line. We've detected early so we can find the root cause. And as we said before, we then have this culture change. The idea that workers are involved to detect problems early, identifying problems, bringing attention to them, and being rewarded for that rather than having that considered like that that's their problem. And you can design your process so that you have built-in tests, monitoring that can signal these problems quickly and automatically, and very importantly, immediately. And finally, preventing defects. Well, there's a lot of costs going into preventing, but you've got to make sure that you have the right type of, as we were just saying, automatic checks. You've got to put the time in. If you just have an inspection at the end of the process, you've got these non-value added costs and capital just for the inspection. And of course, you still end up with scrap or rewear costs, rather than having prevented the defects all the way at the beginning. And inspection is never perfect. As we were talking about the external failure costs, you can end up, some of those defects may slip through, and that can be then lead to very large problems when the defects get out into the field. Additionally, again with the idea of culture, inspecting at the end removes responsibility. And again, not that we want to finger point, but as soon as you find where the defect occurs, you can look at it and attack it right away rather than waiting until the end. And you can end up quite often finding that you have a bottleneck in your process just at the end, at the inspection point. So prevention typically costs less than the combination of all the inspection, internal and external failure costs. And how do you do this? You want to develop capable business processes through standardization and continuous improvement, for which is our goal of Six Sigma.